Scene script. Have you ever wondered how a single particle can exist in two places at the same time? In the realm of the microcosmic, where atoms and particles dance, there exists a dazzling, perplexing universe that defies the very fabric of our common sense. This universe, my friends, is the domain of quantum physics. Quantum physics is no ordinary branch of science. It's a radical, mind-bending field that challenges our basic understanding of reality. It's a world where particles can exist in multiple places at once, where they can teleport through barriers, or even behave like waves. Imagine a particle playing hide and seek, but in two places at once, or a particle taking a stroll, but as a wave. Sounds bizarre, right? But that's quantum physics for you. Now, you might be wondering, what has this got to do with our everyday life? Well, much more than you might think. The strange and counterintuitive principles of quantum physics underpin the very technology we rely on every day. From the silicon chips in your smartphone to the lasers in your DVD player, they all owe their existence to the mysterious world of quantum physics. Quantum physics isn't just about tiny particles and waves, it's about understanding the fundamental nature of the universe. It's about asking the big questions. What is reality? What does it mean to exist? Quantum physics might not have all the answers yet, but it certainly gives us a fascinating perspective to ponder upon. But don't be daunted. Yes, quantum physics can be mind-boggling. Yes, it can seem abstract and distant, but it's also incredibly intriguing. It's a field that invites curiosity, that rewards exploration, and that promises to continue reshaping our understanding of the universe in ways we can't even begin to imagine. So buckle up and prepare for an exhilarating journey into the quantum realm, where the ordinary rules of physics take a back seat, where logic takes a twist, and where imagination reigns supreme. Welcome to the fascinating world of quantum physics, where the impossible becomes possible. Our journey begins with the tale of a curious scientist and a little light problem. The curtain rises on the dawn of the 20th century with a physicist named Max Planck. Imagine him, hunched over his desk, grappling with a scientific problem that had been vexing the brightest minds of his time: the black-body radiation problem. In simple terms, a black body is anything that absorbs all radiation that hits it. The problem was that classical physics predicted that a black body should radiate infinite energy, which of course didn't match up with real-world observations. This was known as the ultraviolet catastrophe, and it was a thorn in the side of physicists worldwide. Enter Max Planck. In a bold move, he proposed that energy is not continuous, but instead comes in discrete packets, which he called quanta. This was revolutionary. It went against the grain of classical physics, which held that energy was a smooth, continuous wave. Planck suggested that the energy of these quanta was directly proportional to the frequency of radiation. The higher the frequency, the higher the energy of the quanta. This simple yet profound idea solved the blackbody radiation problem. The predicted infinite energy crisis was averted, and Planck's theory matched the observed data. But it did more than just that. This concept of quanta laid the foundation for a whole new branch of physics. It was a radical departure from the deterministic laws of classical physics and introduced a world where probabilities reigned supreme. This was the world of quantum physics, a realm where particles can exist in multiple states at once, and actions can influence others instantaneously, regardless of distance. And thus, quantum physics was born, opening a door to a brand new world of possibilities. It was a world that would challenge our understanding of reality and change the way we perceive the universe. It was a world that was waiting to be explored, and that exploration had just begun. Imagine leaping from one cliff to another without crossing the space in between. Sounds impossible, right? But in the quantum world, this is not only possible, but it's also an everyday event. Welcome to the concept of the quantum leap. Picture a bustling city with skyscrapers of varying heights. Each skyscraper represents an energy level of an atom, and the electrons are the city dwellers. But there's a catch. These city dwellers don't use elevators or stairs to move from one building to another. Instead, they disappear from one skyscraper and reappear in another, with no evidence of them existing in the space between. This is what we call a quantum leap. But why do electrons behave in such a strange way? It's all about energy. Electrons inhabit specific energy levels in an atom. When they absorb energy, say from a photon of light, they get excited and leap to a higher energy level. But they don't climb there gradually. They vanish from their initial level and instantaneously appear at the higher one. And what's even more fascinating is that this leap isn't random. electrons can't land just anywhere. They can only occupy specific energy levels. So, if an electron absorbs a photon's energy, it will jump to a higher energy level that exactly matches that energy increase. Now, you might ask, what happens when an electron comes down from a higher energy level? Well, it does another quantum leap, this time to a lower energy level. And in doing so, it releases energy, often in the form of light. That's why, when you heat a gas or look at a neon sign, you see vivid colors. Each color corresponds to a specific energy difference between two levels in an atom. So, in the quantum world, electrons are like teleporting superheroes, hopping from one energy level to another without crossing the space in between. And while this might seem like something out of a science fiction novel, it's actually the science that powers our universe. In the quantum realm, teleportation is not just a sci-fi concept, but an everyday reality. How certain are you about your certainty? This question might seem a bit puzzling at first, but it's at the heart of a fundamental concept in quantum physics known as Heisenberg's uncertainty principle. So, what is the uncertainty principle? Named after the German physicist Werner Heisenberg, it's a cornerstone of quantum mechanics that states it is impossible to simultaneously measure the exact position and momentum of a particle. Imagine you're trying to look at an electron under a microscope. The more precisely you try to pin down its location, the less you know about its speed and direction, and vice versa. It's like trying to catch a hummingbird in flight. If you focus on where it is right now, you have no idea where it's going next. But if you try to predict its flight path, you lose track of its current position. Now you may ask, why is this? Well, it's not because our instruments aren't precise enough or our techniques are flawed. It's a fundamental property of the quantum world itself. You see, particles like electrons aren't just tiny billiard balls bouncing around. They also exhibit properties of waves. And just like you can't pin down a specific point in a wave, you can't pin down a particle's position and momentum at the same time. This might sound counterintuitive, especially when compared to our everyday experiences. In the macro world, if you throw a ball, you can predict exactly where it will land based on its initial velocity and direction. But in the quantum world, things don't work that way. Here, precision gives way to a world of probabilities. You can only predict the likelihood of finding a particle in a particular place or moving at a certain speed, but you can never be completely certain. So, Heisenberg's uncertainty principle isn't about our inability to measure. It's about the fundamental nature of the universe itself. It tells us that at the quantum level, things are fuzzy, unpredictable, and full of potential. In the quantum world, certainty gives way to probabilities and possibilities. What if I told you that two particles could communicate instantaneously, no matter the distance between them? Welcome to the whimsical world of quantum entanglement, where the ordinary rules of time and space take a back seat. Let's consider a pair of particles that have interacted in a way that their quantum states are intertwined or entangled. Imagine these particles as two perfectly synchronized dancers. No matter how far apart they are, they move in harmony, with each one instantly reflecting the other's moves. This is what happens in quantum entanglement. The state of one particle is directly connected to the state of the other, regardless of the distance between them. But how can this be? How can the information travel instantly between the particles without breaking the speed limit of the universe, the speed of light? It's a question that left even Albert Einstein scratching his head. He famously referred to it as spooky action at a distance. You see, in the quantum world, things don't necessarily behave as we might expect them to based on our everyday experiences. Indeed, the reality of entangled particles challenges our understanding of the universe. These entangled particles are not just sending information to each other. Instead, their states are inexplicably linked. Change the state of one, and the other changes instantaneously. Quantum entanglement is more than just a theoretical concept. It's a fundamental aspect of quantum mechanics that has real-world applications, from quantum computing to quantum cryptography. Still, the concept of quantum entanglement remains one of the most bizarre and fascinating aspects of quantum physics. It's a phenomenon that continues to puzzle, perplex, and astound scientists and laypeople alike. So the next time you marvel at the wonders of the universe, remember that beneath the surface, there's a world where the impossible becomes possible, where particles can be in two places at once, and where, as we've just learned, distance is no obstacle for connection. Entanglement, the spooky action at a distance, pushes the boundaries of our understanding of the universe. Is the cat dead, alive, or both? This question serves as the premise for one of the most intriguing thought experiments in quantum physics: Schrödinger's cat. Picture this. A cat is placed in a steel box along with a radioactive substance, a Geiger counter, and a vial of poison. If an atom of the radioactive substance decays, it triggers the Geiger counter, which then shatters the vial, releasing the poison and killing the cat. Now, until the box is opened, we don't know whether the atom has decayed and the cat is dead, or the atom hasn't decayed and the cat is alive. In classical physics, the cat would be either alive or dead, but quantum physics tells a different story. According to the principle of superposition, the cat is in a state of being both dead and alive at the same time, until someone opens the box to observe. Sounds confusing, doesn't it? But this is where the magic of quantum physics lies. Superposition allows a quantum system to be in multiple states simultaneously. It's like flipping a coin. Until it lands, it's both heads and tails. The act of observation, or in the case of the coin, the moment it lands, forces the system to collapse into one of the possible states. So what does this mean for our feline friend? Well, until the box is opened, the cat exists in a superposition of states. It is both dead and alive. It's only when we open the box and observe that the superposition collapses into one definite state. But remember, this is a thought experiment designed to question the interpretation of quantum mechanics. It's not about the fate of a real cat, so no animals were harmed in the making of this quantum conundrum. In the quantum world, the cat is both dead and alive until you look. Imagine a computer that could process multiple solutions at once. A wild concept, isn't it? But that's exactly where the field of quantum computing is heading, and the implications are nothing short of revolutionary. In the realm of classical computing, we're used to bits, the fundamental units of data that exist in one of two states, 0 or 1. But quantum computing introduces us to qubits, quantum bits that, thanks to the principle of superposition, can exist in both states at the same time. Imagine being able to read an entire book in the blink of an eye, because you're not just reading one page after another, but all the pages simultaneously. That's the kind of speed boost we're talking about with quantum computing. But there's more. The second principle at play here is quantum entanglement. In the quantum world, two particles can become entangled, meaning the state of one instantly influences the state of the other, no matter the distance separating them. In a quantum computer, this allows for an incredible level of coordination between qubits, leading to even more computational power. These two principles, superposition and entanglement, could utterly transform the field of computing. We're looking at the potential for incredibly fast processing speeds, the ability to handle complex calculations far beyond the capabilities of today's most powerful supercomputers, and the possibility of creating secure communications that can't be intercepted. But let's not get ahead of ourselves. Quantum computing is still in its infancy, and there are many technical challenges to overcome. Error correction, maintaining quantum states, and simply building a practical, workable quantum computer are all hurdles that researchers are grappling with. Still, the potential is there. The promise of quantum computing represents a paradigm shift in technology, a leap forward that could change everything from artificial intelligence to cryptography. Quantum computing could be the next big leap in technology, all thanks to the strange rules of quantum physics. You might be wondering, what does all this have to do with me? Well, quantum physics isn't just a lofty concept reserved for the halls of academia. It's a fundamental part of how we understand and interact with the world around us. The principles of quantum physics are embedded in the very fabric of our everyday lives. Let's break it down. Consider the technology you use daily. Smartphones, computers, even the humble LED light bulb. They all owe their existence to the principles of quantum physics. Behind the scenes, these devices rely on the peculiar behaviors of subatomic particles. For instance, the semiconductors that power your devices would be nothing more than chunks of silicon if it weren't for the quantum magic that allows electrons to move in specific ways. But it's not just about gadgets and gizmos. Quantum physics shapes our understanding of reality itself. It challenges our intuitions and forces us to rethink what we thought we knew about the universe. It tells us that particles can exist in multiple places at once, that they can be both waves and particles, and that they can affect each other instantly across vast distances. These ideas might seem strange, even downright bizarre, but they are the truths that our universe operates on. Moreover, quantum physics isn't a finished story. It's a field of study that continues to evolve and grow, pushing the boundaries of our knowledge and capabilities. The quantum computers of tomorrow could revolutionize industries, from medicine to finance, and even help us tackle some of the biggest challenges facing humanity, like climate change. So, while you may not be conducting quantum experiments in your kitchen or calculating wave functions in your spare time, the reality is, quantum physics is an integral part of your world. It shapes the technology you use, informs the way you understand the universe, and holds the potential to transform our future. Quantum physics might seem remote, but its impact is closer than you think. Despite its wonders, quantum physics is not without its mysteries. Indeed, as we delve deeper into the quantum realm, we encounter puzzles that continue to baffle even the brightest minds. One of these enigmas is the measurement problem. In quantum physics, the act of observation seems to determine the state of a quantum system. Prior to measurement, a quantum particle exists in a state of superposition, embodying all possible outcomes simultaneously. However, once observed, the particle collapses into one definite state. This peculiar behavior poses a question. Why does the act of observation force a particle to choose a state? It's a question that continues to ignite heated debates among physicists. Next, we face the challenge of quantum gravity. This is the quest to reconcile quantum mechanics, which governs the tiny, with general relativity, which rules the large-scale universe. Both theories are incredibly successful in their respective realms. However, when we try to unite them to understand phenomena like black holes or the origins of the universe, they clash. It's like trying to fit a square peg into a round hole. The resulting paradoxes, such as the information paradox in black holes, are a clear sign that our understanding of the universe is still incomplete. This leads us to the third mystery: quantum entanglement. This phenomenon, termed spooky action at a distance by Einstein, involves two particles becoming linked, such that the state of one instantly influences the other, regardless of the distance between them. This seems to contradict the speed limit set by light. How this happens is still an unresolved mystery. These unresolved mysteries are more than just intellectual puzzles. They represent the frontiers of our knowledge, the boundaries that we're striving to push. They challenge our understanding of the universe, prompting us to question, to wonder, and to explore. The mysteries of quantum physics remind us that our quest for understanding the universe is far from over. As we continue to probe the quantum world, who knows what other wonders and mysteries we'll uncover? Our quantum journey has been a wild ride, hasn't it? We've delved into the fascinating yet perplexing world of quantum physics, where the rules of the game are vastly different from what we're used to in our everyday lives. Let's take a moment to recap. We started with the quantum conundrum, the mind-bending realization that particles can exist in multiple states at once. This led us to the story of quantum physics, the history, and scientists who shaped this groundbreaking field. We then leapt into the quantum leap, where we learned that particles can jump from one energy level to another without passing through the space in between. Following this, we uncovered the uncertainty principle, which tells us we can never know both the position and momentum of a particle with absolute certainty. Next, we tackled quantum entanglement, a spooky connection that links particles no matter how far apart they are. And of course, who could forget about quantum superposition and our feline friend, Schrödinger's cat? We also explored the revolutionary potential of quantum computers, machines that could solve problems faster than any supercomputer we have today. Then we examined how the quantum world impacts our lives, from the technology we use to the very fabric of our existence. Finally, we discussed the unresolved mysteries of quantum physics, the questions that continue to baffle and intrigue scientists today. But our journey doesn't end here. There's so much more to learn, to question, to explore. Quantum physics is an ever-evolving field, with new discoveries and theories emerging all the time. The quantum world is a vast, uncharted territory, and we've only just scratched the surface. I encourage you all to keep delving into this fascinating realm. Stay curious, keep asking the tough questions. After all, the greatest discoveries often come from the most unexpected places. Remember, every great discovery starts with a simple question. So keep wondering, keep exploring, and who knows, you might be the next quantum pioneer.